We concluded the last lecture with the general steps to be followed in quantizing a classical system. Now, we will follow these steps to obtain the quantum field theory from classical scalar field theory. For a classical scalar field theory, the action is given by minus 1 by 2 integral d for x partial phi plus m square phi square, and the corresponding equation of motion is this. We have already calculated. The canonical momentum density pi is given by phi dot, and the Hamiltonian density is pi square by 2 plus half gradient of phi square plus half m square phi square. Now let's solve this classical equation of motion. Because of the translational symmetry of the equation of motion, it is very easy to solve this differential equation in the Fourier space. The classical equation of motion can be solved using Fourier transform, and the solution is given by phi of x is equal to exponential of minus I e t plus I k dot x. Okay, so it is a plane wave solution, and here energy E is square is given by m square plus k square, and this is omega k square. Okay, so E is equal to h cross omega, right? And h cross is taken as 1 in natural units, therefore E is omega k and E square is omega k square. Now I can also write omega k is equal to plus or minus root of m square plus k square, okay, from the equation for energy. So therefore we normally separate the positive and negative roots of omega. So here you can see there are positive and negative roots available for omega, and in general it is a convention to separate them into positive and negative roots. Okay, therefore I can write the positive energy solution for phi as uk of x is equal to e raised to minus I omega k t plus I k dot x, and the negative energy solution I'll write as uk star of x is equal to e raised to I omega k t minus I k dot x. Okay, so this is the positive energy solution and this is the negative energy solution, and the complete basis is formed by both uk and uk star. So using the basis, the most general classical solution for phi of x is given by integral by 2 pi cube 1 by root of 2 omega k ak uk plus ak star uk star. Here ak and ak star are full set of integration constant for all k. Okay, so these are the full set of integration constant. If you want to promote this solution to quantum mechanics, then we have to promote the operator, right? The constant AK to the operator AK, and the constant AK star to the operator AK dagger. And phi of x, the field phi of x will be an operator phi cap of x. Then phi cap of x is equal to integral dqk by 2 pi cube 1 by root 2 omega k ak uk plus ak dagger uk star. Okay, so once you obtain the operator, then we have to impose the canonical commutation relation. Okay, so next we'll impose the canonical commutation relation. In quantum mechanics, if you have a single particle, then the commutation relation will be x cap p cap is equal to I. And if you have multiple particles, then I have to represent x as xa, where a is equal to 1, 2, 3 up to n. So if there are n particles, then it will go up to n. Okay, similarly, the momentum is also represented as PA. If there are more particles, then you have to label each particle, right? In that case, the commutator relation will become XA of t, comma, PB of t is equal to I delta AB. Okay, so this is nothing new, this is just the generalization of what you have learned, like x px is equal to I, right? So y py is equal to I, and similarly if you have a cross term x and a py, then this will be 0. This we have already learned, so I am just generalizing it. Okay, I'm just generalizing it by using the Dirac delta. If they are the same, if A is equal to B, then the Dirac delta will be 1. Otherwise, if A not equal to B, then the Dirac delta will be 0. So I'm just generalizing the commutation relation. Okay, so it's just like A and B in quantum mechanics. In quantum field theory, we have primed and unprimed dynamical variable. Okay, from classical field theory, we can guess the commutation relation in quantum field theory. For example, phi t comma x and phi t comma x prime will be 0, right? Similarly, pi t comma x, and here pi is operator, so t comma x prime is equal to 0. So this we can easily guess because the commutation of same operator, because phi minus phi will be 0. Similarly, pi minus pi will be 0. So no need to deduce the commutator relation if the operators are same, because by analogy we know that it will be 0 because it's the same operator, right? but we don't know what is phi and pi. So how do you deduce this one? And all you know is that XA and PA commutation will give you I delta AB, right? So the analog here is phi cap and pi cap. So what is this? So if you directly take the analog from quantum mechanics, then I can write this will be equal to 0 if x is not equal to x prime, and this will be equal to I if x is equal to x prime. Okay, if this is so, then what comes to my mind immediately is Dirac delta. So I can just represent it by Dirac delta. But if I think more deeply, then the question arises as to why it should not be derivatives of Dirac delta or square. Why not square or cube of Dirac delta? Why should I write just Dirac delta? It can be either derivative of Dirac delta or Dirac delta square or Dirac delta cube, right? I can write anything here. So this confusion can be resolved through dimensional analysis. Okay, so I'll just do the dimensional analysis of, first I'll start with the action. So if you look at the action must be dimensionless in the natural units that we are using. Okay, so the action is S is equal to minus 1 by 2 integral d for x partial derivative plus m square phi square. So in natural units, the action must be dimensionless. The dimension of action must be right. Action must be dimensionless in natural units. So we consider natural units h cross equal to c equal to 1. So the dimension of h cross is ml square t raised to minus 1, and that must be equal to the dimension of speed of light. Okay, so we can cancel t raised to minus 1, then ml is equal to 1 and m is equal to L inverse. So here we get that the dimension of mass can be equated to the inverse of dimension of length. Also, c is equal to 1 implies LT raised to minus 1 is equal to 1, which means L is equal to T. So length is equivalent to time. Okay, so similarly we can also find the relation between mass and time by interchanging. So these two are important results. Here we have to apply it to the action and see that action is dimensionless. So the left hand side of the action, we know that it is dimensionless. Now we have to apply on the right hand side. So right hand side we have two terms and each term must be dimensionless. So I have to multiply d raised to 4x del mu phi partial phi, right? So first we analyze the first term. So it's enough to analyze any one term. So here this has a dimension of L to the power 4 and del mu means it is with respect to time or partial derivative with respect to x. So it will have inverse length. Field phi, I don't know, so I have to find the dimension of field phi, and again partial, so again L inverse, then again phi. Okay, so this must be dimensionless. So here I can see L raised to 4 minus 1, again minus 1, dimension of phi square is equal to 1, which means L phi is equal to 1, and the dimension of phi will be L inverse. So this is how we find the dimension of the field to be inverse of length. The canonical momentum density, we have already seen that it is equal to phi dot, which means partial derivative with respect to time phi. Now the dimension of momentum will be 1 by L multiplied by L inverse, which is 1 by L, which is L raised to minus 2. So what will be the dimension of the commutator? So phi t of x and pi t of x prime. So we have seen that for field it is length inverse, and for momentum it is L raised to minus 2, which means the dimension of the left hand side of the commutator is L raised to minus 3. Therefore on the right hand side also I need the dimension to be L raised to minus 3. Therefore here I introduce Dirac delta 3 times. Fine. So one Dirac delta has a dimension of 1 by L. So 3 times del cube, in the sense it will be L raised to minus 3. So both left hand side and right hand side will have the same dimension. Okay, I hope this is clear. Therefore I write the commutation relation between the field and the canonical momentum as I del cube x minus x prime. Now I can directly plug the expressions for the field to find the commutation relation between A and A dagger, right? I have to find. So next, what is my aim? My aim is to find the commutation relation between A and A dagger. But here it will be AK and AK prime dagger. Okay, AK comma AK prime dagger. So here there is an issue. You cannot directly find the commutator because here the modes are not the same. Here you have AK and AK prime. So there are two modes. Therefore, in the solution we have to do a mode separation. Mode separation is required. Or in other words, I can say we have to decouple the equation in K. We have to decouple the equation in K. Okay, and then you have to solve it as a regular system of equations for AK and AK dagger. So phi here what I have is in terms of the position. Phi of x is equal to integral d cube k by 2 pi cube 1 by root of 2 omega k ak uk ak dagger uk star, and the momentum is the time derivative of the field, which is phi dot. Therefore it will be integral by 2 pi cube 1 by root of 2 omega k. Now derivative of uk and uk star, so that will be ak multiplied by minus I omega uk plus ak dagger I omega k uk star. Okay. So I cannot directly plug in these two equations. I have to decouple the equation in k, because if I want phi of x, then I can directly use it, and if it is phi of x prime, then here it will become k prime. So the equation is both mixed in k and k prime. So I don't want any mixing, I need separate. For that I have to do the Fourier transform of phi of x and phi of x in k space, into the k space. So the Fourier transform is defined as Fourier transform is defined as okay, the Fourier transform of any function f is defined as integral d cube x multiplied by e raised to minus I k prime dot x multiplied by f of x. Okay, so here the Fourier transform of f of x will be f of k. So f of k is defined as integral d cube x e raised to minus I k prime dot x f of x. So I have to find the field phi of k. Okay, so phi of k will be integral d cube x e raised to minus I k dot x k prime dot x multiplied by f of x. F of x is here phi of x. So phi of x is integral d cube k by 2 pi cube 1 by root of 2 omega k ak e raised to minus I omega kt plus I k x. Okay, this is uk of x plus ak dagger multiplied by uk star. Uk star will be e raised to I omega kt minus I k dot x. Okay, so this is the Fourier transform of phi of k. So now I have to solve this equation. I can multiply this e raised to I k dot x, all the exponential together, right, into these two terms I can multiply. I can take it inside the bracket and multiply to each term. Then I'll get integral d cube x integral d cube k by 2 pi cube 1 by root of 2 omega k. Now inside the bracket I have ak multiplied by e raised to minus I omega kt Then I have ikx and minus ik prime x. Okay, so that will be e raised to I k minus k prime dot x plus ak dagger e raised to I omega kt e raised to minus I k plus k prime dot x. Okay, and I have the integral, standard integral integral d cube x e raised to I k dot x is equal to 2 pi cube del cube of k. Okay, this is the standard integral for Dirac delta. So if you see this above equation, here also I have a standard integral. See, d cube x is here. So d cube x is here and e raised to I k dot x form is here. So I can do the integration using this standard integral. I'll try that. So this is equal to integral d cube k by 2 pi cube 1 by root of 2 omega k. Now ak e raised to minus I omega kt I can take outside, then it will be integral of d cube x e raised to I k minus k prime dot x plus ak dagger e raised to I omega kt, then integral d cube x e raised to minus I k plus k prime dot x. So d cube k by 2 pi cube 1 by root of 2 omega k ak e raised to minus I omega kt, then I'll get 2 pi whole cube k minus k prime. Okay, so from here you'll get k minus k prime plus ak dagger e raised to I omega kt 2 pi cube del cube of k plus k prime. Now 2 pi cube I can cancel, right? Then integral d cube k 1 by root omega k ak e raised to minus I omega kt del cube of k minus k prime plus ak dagger e raised to I omega kt del cube of k plus k prime. Now I have to integrate with respect to d cube k. So I'll take the constants outside. So if I take the constants outside, I'll get 1 by root 2 omega k. Okay, and here if I want to integrate del cube, then here k minus k prime must be 0, which means k must be equal to k prime. Okay, otherwise k prime must be equal to k. So here k prime must be equal to k. So in this first term, wherever there is k prime, I can put it instead k. So it will be ak e raised to minus I omega kt, right? And integral of del cube will be 1 plus, now in the second term k plus k prime must be 0, which means k prime must be equal to minus k. Therefore I write a minus k dagger e raised to I omega kt. Okay, then integral of del cube will be 1. Therefore I get phi of k. Okay, the Fourier transform, after Fourier transforming the field phi of x, I will get phi of k, which is equal to 1 by root 2 omega k ak e raised to minus I omega kt plus a minus k dagger e raised to I omega t. Okay, so this is the Fourier transform of the field. Now similarly, using similar steps, I can also find out the Fourier transform of the momentum density pi. Okay, so before that I'll just write down the equation that I have, the standard equation that I have used in the last step. Integral k minus k prime is equal to 1 if k equal to k prime and 0 if k not equal to k prime, right? Yeah, similarly for k plus k prime also. So following a similar method, I can also find out pi of k. Okay, so this I am not doing it in detail. I hope all of you followed the previous steps and you can just do it yourself and get the equation. Pi of k is equal to minus I under root omega by 2 ak e raised to minus I omega kt minus a minus k dagger e raised to I omega kt. So I have just obtained the Fourier transform of both field and the momentum. Now I have to decouple this equation for k and minus k. Okay, so the importance of this equation is that here, see, for phi you have k and minus k, right? So in the previous equation you had only k, so you cannot find the commutation relation using such a phi, okay, which has only one mode. So you should have multiple modes so that you can do the commutation. So now I have to decouple k and minus k, so that's the next task. Let this equation be equation number 1 and let this be equation number 2. So how do I decouple? If I have 1 and 2, then adding equation 1 and equation 2, then the second term will vanish because here there is a plus and here there is a minus. So how do I do this? So first I have to root 2 omega k phi cap. So root 2 omega k phi cap is equal to ak e raised to minus I omega k plus a minus k dagger e raised to I omega kt. Okay, and second equation I can write under root 2 by omega k minus I pi of k is equal to ak e raised to minus I omega kt minus a minus k dagger e raised to I omega kt. Now if I add these two equations, then I can eliminate the second term, okay, and I'll get 2 ak e raised to minus I omega kt is equal to root of 2 omega k phi plus minus I root 2 by omega k pi of k. So from here I can get ak. ak will be root of omega k by 2 phi of k plus I 1 by 2 omega k pi of k. Rearranging this equation. Now if I subtract these two equations, if I subtract these two equations, then I can eliminate the first term and I will get the summation of these two terms. Okay, I'll write. Then I can get ak dagger it's a minus k dagger. Okay, a minus k dagger is equal to phi of k minus I root of 1 by 2 omega k pi of k. So now I have decoupled the equations. Okay, the modes are different now. And now in Fourier space you have to find the commutator. So phi of k comma phi of k prime will be the Fourier transform of phi of x and phi of x prime. So which will be Fourier transform of 0, which will be 0. Similarly, for momentum, we have pi of k prime commutation will be the Fourier transform of pi of x prime, which is Fourier transform of 0, which is 0. Similarly, phi of k, pi of k prime. How do you find the commutation? This will be the Fourier transform of phi of x prime, which is equal to Fourier transform of x to k and Fourier transform of x prime to k prime I del cube of x minus x prime. Okay, so this will be I am taking outside Fourier transform for x to k. X to k will be integral d cube x e raised to minus I k dot x multiplied by next Fourier transform d cube x prime e raised to minus I k prime x prime of del cube of x minus x prime. Okay, so first I'll solve the first integral and then I'll use it to solve the second integral. So first integral, the result will be e raised to, because here del cube x minus x prime will survive only if x is equal to x prime. So if I substitute, then I will get e raised to minus I k prime of x. A function multiplied by the Dirac delta integration will be the function itself, right? So that is the standard integral. Now I have to do the second Fourier transform. So here it will be I integral of e raised to minus I, if I take outside, it will be k plus k prime dot x d cube x. So this will be Dirac delta. Okay, so this is the commutation relation for phi and pi in Fourier space. So now we have all the necessary ingredients and the much awaited AK and AK prime, and similarly AK dagger and AK prime dagger, then AK and AK prime dagger. I have to find all these. Okay, so for this class we'll stop here and we'll see this in the next class. Okay.